is to take one of these formula problems, 3-SAT, NAE 3-SAT, SAT, and reduce it to a graph problem. But how do we reduce, something involving, clauses and stuff to a graph? Okay. So how do we do that? So the first example is the independent set problem. So I'm going to give you the definition again. Independent set. And I'm going to write it to you for you in a sort of more formal way. That is the set of all graphs and T such that G is a graph and T is a natural number and G has an independent set of size at least T. So this is the independent set problem. So the independent set problem is, given a graph G and some parameter T, decide whether this graph has an independent set of size at least T. And this is not an easy problem. And the reason why it's not an easy problem is because it is NP complete. So independent set is NP complete. First of all, independent set is certainly in NP because I can convince you that a graph has an independent set of size T by just giving you that independent set, and you have just to check that there are no connections between any pairs of points in that set. So the only thing that needs to be done is to show that there is an NP complete problem that can be reduced to independent set problem. And the problem we are going to take is 3-SAT. In other words, given an input to 3-SAT, I'm going to construct for you a graph and a parameter T such that the original formula that constitutes the input to 3-SAT is satisfiable if and only if this graph has an independent set of size at least T. And here is the graph. What you're going to do is, I'm going to give you the formula. The formula is it's a 3-SAT formula, so it's a conjunction of clauses. Each clause has 3 literals in it. So I'm going to have a graph where nodes correspond to the literals in it. So every literal in every clause will contribute 1 node to the graph. For example, here you see x1, x2, x3. These x1, x2, and x3 are 1 node. This guy here are these blue nodes. These guys here are the green nodes. So every literal in every clause will contribute 1 node to the graph. So the number of nodes in the graph is 3 times m, where m is the number of clauses. Number 1. So how am I going to define the edges? First of all, for every one of these clauses, I'm going to make a triangle between the nodes that correspond to those clauses. So as you can see, there's a triangle between x1, x2, x3, the blue guys and the green guys. Moreover, I'm going to put an edge between every literal and its negation, if the negation is also a node in the graph. So here x1 and not x1 are nodes in the graph. So I connected x1 with not x1 and x1 with this not x1 here. So the connections in the graph are either within triangles or between literals and their negations. So that's the graph. So the independent set consists of a graph and a parameter T. So I still need to tell you what the parameter T is. So first of all, how many edges does this graph have? Well, for every clause it has 3 edges. So it's 3 times m edges, plus some number of edges that corresponds to connections between literals and their negations. So we don't know it beforehand. It depends on the formula. But what we do know is that we have exactly 3 m nodes. So what we are going to do is we are going to take for our parameter T the number m, where m is the number of clauses in the. So we are going to prove that 3-SAT is reducible to independent set. And so given a formula F, which is a conjunction of M clauses, construct the graph as given on the slides. And the parameter t is going to be m. So you see, by the way, what is the largest independent set that this graph can have? In this particular case, what is the largest independent set that this graph can have? What do you think? So you look at the triangles. How many nodes in each triangle can you pick in the independent set? One at most. So, and how many triangles are there? M, where M is the number of. So the largest independent set that this graph can have is M. Cannot have more than, the independent set of this graph, the largest one, cannot have more than M elements. And this is what we're going to pick for our parameter. So we're going to show that F is satisfiable if and only if there is an independent set of size at least M in the graph G. And this way we have reduced 3-sat to the independent set problem. So why is this? You see, if F is satisfiable, this means that every clause, that there is an assignment that satisfies every clause. All right? So pick in every clause one satisfied literal. Okay? And what I'm going to tell you, what I'm going to show is that the set of nodes that correspond to these satisfied literals is an independent set. Exactly, but you need to have exactly one. Set of nodes corresponding in G, corresponding to these literals, is an independent set of size M. So the size is M. It's clear because for every clause we picked one. So the size is certainly M. We just need to show that this is independent. So we cannot have two nodes in the graph, so in this set, that are connected to one another. So obviously, within every triangle, it's independent because in every triangle we picked exactly one node. So there's, we cannot, since we cannot have two nodes in the same triangle, the only possible edges between these literals, between the nodes corresponding to these literals, will have to be edges of this type, between a literal and its negation. Right? But if there is an edge between a literal and its negation, it means that this literal was true in one of the clauses and its negation was true in another clause. But this can't be. Right? So only possible edges between the nodes corresponding to these literals are of the form literal is connected to its negation, but such edges don't exist since either lambda or lambda bar is true. So we cannot have picked lambda as a true literal in one of the clauses and lambda bar as a true literal in the other clause. This we cannot have picked because it's impossible. So that's why there is no such edge. So if we have a satisfying assignment, then we have identified an independent set of size at least m. On the other hand, suppose that there is an independent set of size at least m. We just saw, right? If that is the case, then every triangle has to contribute exactly one node to that independent set. No triangle can contribute two, it's clear. So, and there are m triangles, so each triangle gives exactly one node to this. So, on the other hand, if S is an independent set of size m, then it has to be of size exactly m, and each triangle contributes exactly one element to S. And what we are going to do is we are going to pick the value of the literal corresponding to those nodes to be true. Assign true to literals whose nodes are in S. Okay? So now we have picked for every clause, we have picked one true literal. The only thing we need to make sure is that there is no contradiction, that we have picked a true literal in one and a false literal in the other. So you want the other ones to be false. Assign true to literals whose nodes are in S, false to literals whose nodes are not in S. Well, actually this is not quite true, because, I'm sorry about that, because you could have a literal that you have picked in one, and this literal appears in another clause, you just didn't pick it in the other clause, right? Still its value is true. So it doesn't say that the other ones are false necessarily, but definitely the ones that you have picked, you want to give them the value true. So is it possible that we pick a value, a literal, we give a literal the value true in one and the value false in the other? How would this pass? Well, once we have picked the value of a literal to be true, if it appears in another triangle, that value has to be true too. I mean, we didn't change the value. So the only way that we can get a contradiction is to have picked a clause, given it the value true in one triangle, and picked the negation of that clause and given it the value true in another triangle. That's the only way we can get a contradiction then. But is this possible? Can we have picked one node, one literal in one clause to be true, and the negation of that literal in another clause to be true? Look at where they are coming from. They're coming from an independent set. Since they are in an independent set, the nodes corresponding to this S cannot correspond one to a literal and the other to the negation of the literal, because there is an edge between the two. Is that clear? We cannot have picked, the set S cannot contain a literal and its negation, because there is an edge between them and S is independent. So we cannot have ever picked a literal to be true and its negation to be true as well. No contradictions. Because literals are connected to their negations. So cannot both belong to S. So a literal and its negation both be in S. So, yes, please.
Actually, I don't understand why each triangle must contribute one example.
Because we are assuming that we have an independent set of size at least m. Right? We just saw that if we have an independent set of size at least m, its size cannot be bigger than m. It has to be exactly m. Because every triangle can contribute at most one element to this independent set. Cannot contribute two. Because if it did, then these two would be connected. Right? So if we have an independent set of size at least m, it has to be of size exactly m. And every triangle has to contribute exactly one element to that independent set. Because if there is a triangle that doesn't contribute anything, then another triangle has to contribute two. Right? Yes?
I'm a bit confused by the fact that we used a very specific graph.
Yes.
I mean, we showed that this type of graph.
Yes. Yes.
I mean.
Yes.
Solving the
I understand your question.
Okay,
And the answer is because we are doing this kind of reduction. You see, if we wanted to do the other type of reduction, saying that independent set is reducible to 3-sat, then we would have to start with any graph and then construct from this some particular 3-sat formula. So reduction here means you start with any formula. So reduction means if you had a nice algorithm for independent set, you would also have a nice algorithm for 3-sat. And the way you prove it is the following. You take the formula for your 3-sat that you want to show satisfiability of. You create this particular graph. Apply the algorithm, the general algorithm for independent set to this particular graph, and then get the result for. Okay? Okay. So this way we showed that if we have an independent set of size at least m, then we also have a satisfying assignment. So this is NP complete. Now we also showed that independent set, clique, and node cover are equivalent. So immediately we see that clique and node cover are also NP complete. All right. So the next one, in fact the last one for today that I will show you, is max cut. So what is max cut? A cut in the graph is a partition of the set of nodes. So one side is S, the other side is the complement of S. And the value of this cut is the number of edges between these two sides, between these two partitions. So in this case, for example, if this is the graph, then this is S, so the value of the cut is 3, because there are 3 edges that leave S and connect it to something outside S. So I'm going to write that down for you. So G, if this is a graph, a cut is a subset S of the set of vertices, and the value of the cut is the size of the number of edges between S and its complement. You remember this notation. It's the number of edges between S and its complement. So in this particular case, for this cut, the size, the value is 3. So you remember in the flow algorithm, what we showed is there is a polynomial time algorithm for calculating the minimum cut in a graph. Right? So min cut is polynomial time. The way we do it is we put capacities of 1 on the edges and start with some S and some T and calculate, take the Ford-Fulkerson algorithm and run it, and then we get the value of a cut between S and T. And as we vary S and T over all possible choices, we get a minimum cut. Okay, so this is a polynomial time algorithm. However, if you look at max cut, it's as far away as polynomial time as you can imagine. It becomes NP complete. So finding, asking to find the maximum cut in a graph is very difficult, whereas the minimum cut is polynomial time. So the max cut that's the set of all graphs and all parameters k such that G is a graph, K is a natural number, and G has a cut of value K, or size K. Or at least K, sorry. At least K. It doesn't matter whether exactly equal or at least. So it turns out that max cut is NP complete. And for this, we are going to use not all equal 3 set. So it's pretty difficult to say whether a graph has, finding the maximum cut in a graph. And the proof is by reducing not all equal 3 set to max cut. Well, first of all, it is max cut is in NP. That is clear, right? Because, if I've given a graph G and this parameter K, it's very easy to convince you that there is a cut of size at least K. I give you this subset S. And what you need to count is the number of edges that leave S and land in the complement of S. So that's a polynomial time algorithm. That's very simple. So it is in NP. So once we show that there is a reduction from some NP complete problem to this problem, we have shown that it is NP complete. So the reduction is not totally trivial. You need a little bit of work for that. So the way this works is as follows. So we take some formula F. Again, it consists of M clauses. And let's see whether we have pictures here. Here is the picture. Okay. So what we're going to do is we're going to so the graph G has as nodes the variables x1 through xn and the negations x1 bar through xn bar. So this is what the graph G will have as nodes. For every clause, if the clause is lambda I1, lambda I2, lambda I3, introduce triangle in G between the corresponding nodes. In fact, what I'm going to construct for you is not a graph, it's actually a multi-graph. It's a graph with integer capacities on the edges. It's, you can do different things. You can say, max cut with integer capacities, where the graph has integer capacities on the edges. It's not such a big deal. So, here is, and then we are going to so if, let's say, Nj is the number of occurrences, the number of times xj or its complement xj bar appear in F. So what I'm going to do now is a bit different from what you have in your polycopies, because it's a bit easier to understand. We are going to put 3 nj parallel edges between xj and xj bar in G. So in your polycopies it says nj, but I'm going to put 3 times nj because it makes it a bit easier. So let's see how it works. So here we have, let's say the formula consists of these 2 clauses. Then I have the 4 variables and their negations. These are the nodes of my graph. I have x1, x2, not x3, so I'm going to connect x1, x2, and not x3 into one triangle. Then not x1, not x2, and x4, so not x1, not x2, and x4 into one triangle. So how many times does x1 appear? Well, it appears twice. So I'm going to put, in fact, 6 edges between x1 and x1 bar, not 2, 6. How many times does x2 appear? Well, it appears twice. So I'm going to put 6 edges between x2 and x2 bar. Then x3 appears or x3 bar appear 1 time. So I'm going to put 3 edges between x3 and not x3, and 3 edges between x4 and not x4. So that would be my graph then. Okay? All right. So what do we know about the sum of the nj's? What is this sum? So the sum tells you for every j, it tells you the number of times xj or xj bar appears in the formula. So if you go over all the j's, it tells you how many literals are in the formula. So how many literals are in the formula? Each clause has how many literals? 3. And how many clauses? M. So it's 3m. Okay, so how many edges does this graph then have? For every triangle, how many edges does the triangle have? Well, 3. How many triangles do we have in the graph? M. For every clause, we have 1 triangle. So there are 3m edges for the triangles. And how many edges do we have between literals and their negations, or variables and their negations? Well, 3nj for every one. And when we sum everything up, it's 3 times. So this is 12m. So there are 2n nodes and 12m edges. It's not exactly this, because I didn't put 3 times. I just put 1 in this one. Okay, so now I need to show that the original formula, the max cut has another variable, which is the value of the cut. So I'm going to show that f is satisfiable, well, actually NAE satisfiable. Actually, you know what? I don't know why I'm putting 3 times nj. Let's put it just nj. It doesn't really matter, but it doesn't matter. Let's put nj. Doesn't matter. So then we're back to here. Okay. So f is NAE satisfiable if and only if G and 5m is in max cut, meaning that the graph G has a cut of size at least 5m. Let's see. Let's say that f is NAE. Actually, let's look at the Let's look why I'm choosing this parameter 5m. That's interesting to see why I'm choosing 5m. You see, so in a triangle, what can happen in a triangle? So in a triangle, either all the three nodes belong to one side of the cut, which means that the triangle doesn't contribute anything to the value of the cut, or one of the nodes belongs to one side and the two others belong to the other side. Okay? In which case the triangle would contribute two edges to the value of the cut. So the triangles altogether will contribute at most 2 times m edges to the value of the cut, because each triangle contributes at most 2 edges to the value of the cut. So that's 2m edges. So in order to get to 5m, I need still 3m edges. The 3m comes from here. You see, if my xj and xj bar belong to two sides of the cut, then the edges between them there would be nj edges that would correspond to the that would contribute to the value of the cut. So if I can make xj and xj bar to belong to two sides of the cut all together, and make sure that in every triangle there is one element that is on one side of the cut and the two other elements are on the other side of the cut, then I'm done. Then I have created a cut of size 5m. And this is exactly what you would want to do if you wanted to get a satisfying assignment. Namely, the literals or the variables on one side of the cut get the value true, and the variables on the other side of the cut get the value false. That's what you want to do. That's how the whole construction hinges upon that. So what we're going to do is I'm going to construct for you a cut of size 5m, if that happens. 5m is the largest value of a cut. You cannot get anything above 5m. So NA is satisfiable. So I need to construct for you a cut of size 5m. So for this one, I take S is set of all variables, of all elements in x1, xn, x1 bar, xn bar that are true. So the true assignments, they correspond to S. The ones that are picked true in this satisfying assignment, they correspond to the nodes of S. The other ones, the false ones, correspond to the complement of S. So how many edges what is the value of the cut then? What is E of S and this? So how many edges do I have between S and Vs? So you see, so here is where we need the not all equal 3 set. That's very important. When I do this, can I have is it possible that in a triangle all the elements are either in S or in S bar? Is that possible? A triangle corresponds to a clause. This clause has to be not all equal satisfiable. So it cannot be that all the literals in the clause are satisfied or all of them are not satisfied. So there must be one satisfied literal and one not satisfied literal. So every triangle contributes one node to one side of the cut and 2 nodes to the other side of the cut. So F not all equal satisfiable means that every triangle contributes 2 two edges to the cut. We could not have done this if f were not and not all equal satisfiable. So this would be then 2m for these triangles. That's the contribution of the triangles. Now, since we picked the true literals to be in S and the other ones to be in the complement of S, we cannot have picked xi and the negation of xi cannot be both belonging to the same set S. So one of them is on the one side of the cut, the other is on the other side of the cut. So altogether, I'm sorry?
So we have also the sum of nj.
Exactly, that's exactly it. So this would be the sum (5m). So this corresponds to the 5m edges. So if we have a satisfying assignment, that's actually the easy part of the proof. The harder part of the proof is to show that if there is a cut of size 5m, then there is also a satisfying assignment. But I just told you how essentially this works. If you have a cut of size 5m, then every triangle has to contribute, in every triangle, one element is on the one hand, on the one side of the cut, the other two elements are on the other side of the cut. Right? So, what we're going to do, it would be very easy to say, well, take the one element that's on the one side of the cut and say that this is true, and the other two elements are false. The only problem that we may get is that both xj and xj bar may end up on the same side of the cut. This would be a contradiction. So the way we are going to do this is by disallowing that, or massaging things so that doesn't happen. So let S be a subset of this x1, xn, x1 bar, xn bar, and let's say that S vs is 5m. So we have identified the cut. Now I want to construct a satisfying assignment from this. So the way this works is, so without loss of generality, if xi is in S, then xi bar cannot be in S, is not in S. Why? That's the key of the whole thing. The thing is, suppose that xi and xi bar were belonging to the set S at the same time. Now, in total, they contribute at most nj to the or ni. So if xi and xi bar belong to S, they contribute at most ni times ni edges to the cut. And if I put them on opposite sides, putting them on opposite sides, so if they're on opposite sides, then they contribute at least ni edges to the cut, right? So it's always better to put them on opposite sides. So if this happens, so this means, if you have a cut, it doesn't necessarily mean that you have them on opposite sides, but if you just take one of them, put them on an opposite side, you get a better cut. So, or you're not going to change the value of the cut to something worse. So now set the xi's, set the literals in S to true. So what happens now? If you set the literals in S to true, you see S is something that has 5m edges. This means that every triangle has to contribute exactly 2 edges to S. So every triangle contributes 2 edges to S, right? Because if there was some triangle that would contribute fewer than 2 edges, then the total of all the other edges that can contribute would be less than 5m. Because the triangles would at most contribute 2 times m minus 1, and all the other edges are 3 times m, so you cannot get 5m with that. So contribute 2 edges to S, i.e. exactly one node is exactly one node is on one side and 2 nodes on the other side. So this means that the clause corresponding to that triangle is not all equal satisfiable. Because you have one of them is true, the other 2 are false, or one of them is false, the other 2 are true. Okay, so this is true for every clause, so therefore the entire formula is not all equal satisfiable. And that's it. That's the end of the proof. Okay. So that's essentially it for today. Next time we are going to talk about Hamiltonian paths and so next time I don't think I'm going to need more than 45 minutes. So on Monday the class will be only 45 minutes, probably even less. And that's the end of that for the semester. But we will start with Hamiltonian paths next time. Okay, so have a nice weekend then.